All right, what's up, YouTubers? Uh, this on this problem right here, this is like statics and mechanics and just things that follow you for the rest of your life here. But we're going to talk about shear and moment diagrams, and I'm going to talk about that, and I'm going to show you by way of example how we might use that. So in this problem right here, I have a simply supported beam supported at a pin at A and a roller at B. And it's got this distributed load over 8 foot of its length of 200 pound per foot. It's a pretty simple problem. Okay, but I'm just going to highlight the steps that you want to follow when you want to get the shear and moment diagrams. And in this problem asks you to find, the internal shear and moment diagrams. So just a little background, things to remember about shear and moment diagrams, depending on, shear and moment diagrams, it's like you're looking inside. What is going on internally? And so something that's kind of important here is the internal sign convention. Okay, so if I make a cut on the inside of something and I look at the, oh, here, let's do this. If I make a cut, so I have a beam and I make a cut on the inside right here. Here's some cut, and I look at the left side of the cut. My shear points down, my moment goes up. This is a popular positive sign convention, if you will, for and on the right side of the cut, my shear is positive up internally. Moment always causes a happy face, and that's why it's positive bending, because it's happy. It's making you smile, you know, right? And then here, if you want to complete the internal loading, there'd be an axial force causing tension here, okay? So a lot of times what happens, people mix up the shear diagram. So when we draw this internal shear diagram, it's like plotting at every possible point that we can cut, every possible point that we cut, what is the internal shear? Is it positive? Is it negative? What's its magnitude? Blah, 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 blah. All right. So here I'm going to show you how to come up with the ways to do a shear moment diagram. So the first thing you have to do is calculate the reactions. Calc reactions. Don't think you're, don't. Some people think they're psychic, and they can come up with this thinking equilibrium or the reactions just by looking at the thing. The only time you can really do that is if the loading is symmetric and the structure is symmetric. So be safe, draw stuff, right? And so here, they call that a free body diagram. But you got, like, here, I've got a reaction AY, horizontal AX, BY right here, BY. Okay, draw that out on the drawing. Okay, and then apply the equilibrium equation. So you got some of the forces in the X, so some of the forces horizontally in the X, if you will, equals 0. So here AX equals 0. Yes, thank you. That's easy. And then I got to find these other reactions, AY and BY. Those are my unknowns. So here, one of the popular equations without having to get one equation, one unknown, is to use sum of moments. So if I take moments about A, sum moments about A equal to 0, and I say moments are positive going counterclockwise here, then I would have BY times 12 feet right here minus the distributed load resultant. So I'm going to draw a squiggly line here. 200 times 8 is 1,600 pounds of force, okay? That squiggly line is not a replacement of the distributed load. It's just the equivalent resultant, okay? All right, so that is BY times 12 feet. And here, this resultant is 200 pounds per foot, the force times 8 feet, the length. So this gives me that force resultant times the distance from point A to the resultant location, and that is 4 feet. And this is equal to 0. And then I use my spiffy calculator, calculate it out, and hopefully I'm good here. And that number is 533.33 pounds of force. Okay, so the LBF is pounds force. And most of in mechanics, usually you deal with pounds force. It's not like fluids or something else where you have to deal with pounds force and pounds mass or chemistry or something. Here in mechanics and statics, all the pounds that you're going to deal with are pounds force. All right. Then we're going to do some of the moments about B equal to 0 right here, positive right here, and then you might try coming up with that yourself. So minus AY times 12 feet plus 200 pounds per foot times 8 feet times, And this time the resultant from distance from point B here on the right is 8 feet. And that equals 0. And AY in this case is equal to 1,066.67 pounds of force. And you can check my work, but I'm pretty sure I'm good here. Okay. All right. And you know what? I did this problem a little bit earlier, and this, this isn't going to work unless we have a little bit more significant figures, especially for the shear moment diagram. So let's use a little bit more. Okay, we'll use a little bit more. Pounds force right here, and we go down right here. Now we're good. We feel nice about what we've done so far, and what we want to do next is draw the shear and moment diagram. So here, so what I would do is so I redrew I redraw the beam down here, and now, for my shear moment diagram, what I do is, I get my trusty straight edge, so my drawings look good, and I take my straight edge over here, and I draw a nice little line. Oops, no, I don't want that. I want the pen function right here. Draw a line here, and I draw a line here at the supports. And what I'm doing is I want to draw a line wherever I have a discontinuity or something significant happens. Something ends or begins, or I have a concentrated load or something, a moment or axial force. So here, I have a reaction force here, or concentrated load. A distributed load starts and it ends over here. Okay, so I draw these lines where I have those things occurring. Whoa, okay, right there. All right. Oh man, my shear diagram's not gonna. My moment diagram might not fit. And then I draw a line here to indicate my shear diagram. And let me see if I can scroll down a little bit more. And I'll draw my moment diagram down here. Yes. Don't be lazy. Do a good job. Draw straight lines. Use a straight edge. Right. It's not that bad. Okay. So here, bam. Okay, so here, this will represent my shear diagram. Let me draw the line for the shear diagram. I'm going to draw it closer to the moment diagram here. Bam, right here. Okay, I have this, and I have this. I want to make it look clean and nice because I want a professional presentation. Yeah, la 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 la. Okay, and then I have here, I have this. I want to draw my shear diagram here. So my shear diagram right here. And the key is, with this, the way, unless you really understand what's going on, you probably want to follow general rules until you get a really good understanding of what the heck is going on. But here, in this case, you remember that here, this dv dx is equal to minus w. And this is a popular equation that relates the slope of the shear diagram to the value of the distributed loading. Okay, or the negative of the distributed loading. And depending on how you derived it, you have a negative sign or a positive sign there. Okay, a lot of textbooks have this negative sign here. And then that the derivative of the moment, or the slope of the moment diagram, is equal to the shear value, the value of the shear. Bam. And this works going left to right, if you will, going left to right. Okay, and so that's important, and you kind of want to follow that. And so here, let's tell this story going left to right. Okay, so here, for the shear diagram, here at this point, I start 0. My AY was 1066.67. So I'm going to say, all right, I go up here. So I go up to 1066.667. And these are all in units of pounds force right here. And then I go and and what this does, and for me, the way I look at it, is that this is 200 pounds per foot. That equation that said dv dx equals minus w indicates that the slope here is negative, okay, or negative 200. The slope at this point is negative. That tells you that it's decreasing. The way what I use to remind myself is going left to right. Once I put my shear here, this distributed load is kind of pushing me down, all right? And so here I have this 200, I'm going to go down at a rate of 200 pounds per foot. So really, the change that I'm going to have also, if I rearrange this, essentially dv WDX right here, if I erase this, that says that my change in shear is equal to the area under the distributed load. Okay, so this looks like an integral, which is an area. Okay, blah blah blah. And this is an area. So this is like my change in shear is the area under the distributed load. So if I look at this area right here, this is 200 times 8. This is 1,600 pounds, right? 200 times 8, 200 pounds per foot times 8 foot, 1,600 pounds force. That means I'm going to decrease 1,600 pounds. That goes all the way down to negative 533.33 right here. So that means I'm going to have a line going right here. That's constant slope because my distributed load is uniform. And this point right here to here, this point, this is negative 533.333. And then I have no loading from here to here. I have no loading from the end of the distributed load to the other support. And so that makes this right there minus 533.333. And this reaction at By pushes me back up to 0. Okay? Pushes me back up to 0. Yes. Right? Now, that's great. Okay, life is good here. Okay. So some points that are important that are really important is when the shear is 0 here. That's important because shoot, that's like a critical point in calculus, or it's a maximum for my moment diagram. All right. And so here I go. I want this distance. The way I can calculate this distance right here, x, is if you think about this, I'm decreasing this. I'm going down at a rate of 200 pounds per foot. This x is, I start at 1,066.67. How long does it take me to get to 0? And that really is just 1,066.667 divided by 200 pounds per foot. And this is pounds. And this, if you look at this equation right here, it's like, my pounds cancel out. I'm going to have units of feet or distance. And this distance is 5.333 feet. Okay, 5.33 feet. And then this distance right here is 8 minus 5.333 feet, which is 2.667 feet. Yes. Okay. And now, if I want to look at that, right? So I have this right here. Okay. So that's great. All right, so now I look over here. I want to draw my moment diagram. So these distances are nice to have for my moment diagram. I want to draw my moment diagram. So M, the units of this moment diagram are going to be pound force feet. Okay, all right. And here at the support, I have no moment at point A. Okay, I don't have a concentrated moment. I don't have a moment from a reaction or anything like that. So this moment starts at 0, 0. Okay. I also know that dm dx equals v. The value of the shear is equal to the slope of the moment. At this point, right, at this point, I have a positive shear value of 1,066.67. Positive. That implies that it's increasing. It's increasing, okay? And then here, at this location, right here, I have right here, my shear is 0. So that means at this point here, I should have a slope of 0 on my moment diagram. Okay. The other thing we know is that if my shear diagram is linear, then my moment diagram in this region is parabolic. Okay. And I know that this moment diagram should go like this. Okay. So the mistake that a lot of people make is sometimes they'll draw it like this right here. And the only way you know if it's this curve or this curve is by looking at the values of the slopes, and figuring out that, hey, it's increasing from 1.2. It's increasing right here, and it's 0 right here, and that tells you the shape of the curve is right here like this. Okay, so here's my maximum right here. How do I know what this value is? This value right here, just like here before, this value is the change in moment is equal to the area of the shear diagram. Okay, the area of the shear diagram. So that means that this location, this area right here, 1/2 the base times the height. This area is like 2,844.27 pound feet, or 0.3, whatever. Okay, some number. Pound force times feet. That's the area of this. 1/2 base times height. Okay, that's a no-brainer. So right here, this is 2844.3 pound-feet. Then I'm going to decrease this. So here now I have a zero slope and I'm going to a negative slope. That means over here at this point, right here, I have like a negative, I should have a negative slope somewhere. The change in moment from here to here is going to be this area here, this negative, or this negative area right here. And that area, by 1/2 base times height of this triangle right here, of that triangle, comes out to 711.1 pound-feet. Pound-feet. And so I'm going to subtract from here this change is going to be 711.1 pounds force feet. Okay, that's going to be that change right there. So that means it's going to be 284.4.3 minus the 711.1. So I decrease parabolically to this value, which is 2133.7 pound feet. Okay, is that right? Yeah, that looks 2133. Let's just go with 2133. That I think that'll be enough for us. Okay, let's go with 2133. Okay, we don't need to be fancy. Let's go with 2133 right here. And then I look at this area. So again, I'm continuing to decrease. My slope right here is negative 533. That's why it looks like that. And then I decrease this area here, which this area should be about 2133. Okay, this is 2133 pound-feet, and that means I return from here, I decrease 2133, which means I go linearly to 0. Okay, and the slope here should be the same, except here, this is a straight line. This is a straight line right here, and this is parabolic right there. And this video has been too long. Okay, I probably spent too much time on the equilibrium, so you might want to fast forward through that. Okay, and then just bam, draw that shear moment diagram. So you see here, just real fast, this change is 2133 based on this number. Oops, right here. Okay, 2133, and that gets us back to. And this is our shear, and these are our shear and moment diagrams. All right. Hopefully it was helpful. Let me know if you have any questions. Bye.